Hello, DroidCon. Today we're going to be talking all about coroutines. But before we do that, I want to take a moment. Let's all do a round of applause for the organizers for putting this awesome event together. This is like one of the best venues I've ever been in for a conference. This is an amazing place. I love the community that I've interacted with all day. This is absolutely an amazing conference, and I'm so excited to be here. So let's just jump right into coroutines. Got a lot to cover today, and I know we're all very excited to get to that party. So I want to give credit for that title, that beautiful punny title, to this tweet by Thomas, full credit where credit's due. This is just a one-off tweet that turned into a keynote title. Strange things happen on Twitter some days. So the question that is on my mind, like coming into April 2019, are coroutines a fad? Is this some new technology that is, going to kind of pop up and be really cool for about 2 years, and then maybe we're all going to forget about it because it didn't actually solve anything we were trying to fix? And I think we can all think of a technology maybe that we've used in the past that has kind of done this for us. And there's a couple indicators that maybe this is what's going on. So one question I have for the audience, who here's heard about or talked about coroutines in Android in the last 6 months? So that's literally everyone. So who here was talking about or reading about coroutines in Android 2.5 years ago? Who here has a graduate degree in computer science? No, okay. But yeah, so there was one person that raised their hand for the second question versus no one or for everyone for the first question. And that's that's something to as a pragmatic programmer, kind of raises some alarm bells. Maybe this is just one of those technologies that comes and it's going to go. And one of the things that I think is really instructive to look at when evaluating a technology like this is what problem is it trying to solve? What problem are coroutines effective at solving? And then what problems are they maybe not so effective at solving? It's something we could use for everything, but maybe we should use it for specific things. And the problem that coroutines help us solve is by simplifying async programming by replacing callbacks. So there's kind of a lot going on here. But the key that we're really trying to accomplish with coroutines is replace callbacks with something else. And we're going to do that whenever we're trying to do async programming. We'll talk a little bit about what async programming is in the coming slides. But this is really the core of what coroutines give you as an application developer. So let's kind of dive in. What is async programming? So one way to write, I've written this little block of code here that makes a network request and then shows the result of that network request onto the screen. So I can write this in a blocking style. This is called a blocking style or synchronous code, where when I call the network request function, it returns the result right away to my function, right? And so when I do this, it kind of has to block a thread. And for fun, I'm actually going to run this on the main thread, and let's see what happens. So I'm going to go ahead and make that network request call, and then the main thread is blocked the entire time that network request is out. And this is kind of a problem for our Android app, right? So this is something that needs to be handling on draws, doing animations. It needs to be handling touch events from the user. And this network request might take 400 milliseconds. It might take 20 seconds. And that entire time, your app's going to be completely frozen and unresponsive to the user. There's nothing particularly wrong with blocking styles of network calls. But on Android, this isn't what we want to be doing on the main thread. So one solution to this is to introduce async code to our code base. And we can do that by adding callbacks, right? So now I'm still calling network request. I'm still on the main thread when I call network request. But instead, I'm going to give it a callback so that it can call back into my code when that network request is done. Now, let's take a look at how this executes. So I'm going to make that network request. I'm still on the main thread when I make the request. And now, because I gave it a callback, the main thread's actually going to get unblocked during the duration of that network request. And the networking library is responsible for finding some networking thread out there to run that request off of the main thread. And then when it's done, it uses that callback to call back into my code and continue showing the result to the user. This is kind of the core of asynchronous programming. So now I want to translate this callback style. I want to show that exact same function with coroutines. So if you've never seen coroutines before, this probably looks like it blocks the main thread. So I'm going to do the same thing. I'm going to call this function on the main thread, and let's see how it executes. So I'm still going to call it on the main thread, but this time I'm going to color it green instead of red for some reason. And then it's actually going to unblock the main thread immediately when it calls that network request function. The networking library is still responsible for finding a thread to execute that network request. And then when it's done, it uses some mechanism to actually go ahead and pass that result back to me. And that mechanism is coroutines. Like this is the core of coroutines right here. So in order to make this a coroutine, in order to say execute this as a coroutine, I had to basically make one change. I had to say this is a suspend function, which I appended to the beginning of my function. So this right here is kind of the core of coroutines. And that thing at the beginning, when it kind of unblocked the main thread, that's suspend. So that's a suspend operation. It's a new thing a function can do. So functions like that we're used to you can call a function and you can return from a function. In a suspend function, a function can also suspend itself. And then later, the thing that it did to pass the result back, that's resume. That's another operation on functions that's added in order to implement coroutines. And one way to think about what a coroutine is doing for you is to kind of like map coroutines to callbacks by thinking about when I call that suspend function network request, I'm kind of creating a callback to the rest of my code. Like the rest of the function after network request just automatically becomes a callback. This is a good way to kind of map between the two different concepts. And you can kind of think of this as suspend and resume gives us a mechanism to replace callbacks. And we can even like write that. Like, so this is the suspend version, and this is the callback version, right? So these are going to execute in very, very, very similar ways, even though the code looks very different. And the suspend version is just a little bit simpler, a little bit easier, especially if I start calling multiple network requests here. So let's turn that back into a coroutine and take a look at this network request that we've kind of been eliding so far in the talk. How does that thing work? How's it actually finding another thread? How's this whole thing working? So I'm going to make another suspend function. It's called network request here. And then inside that function, I'm going to call this like super magic function that's just amazing on Android. It's with context, and I'm going to tell it dispatchers.io. And let's just dive in here. So dispatchers.io is one of 3 dispatchers that Kotlin coroutines gives us as Android developers out of the box. The other 2 are main and default. And you use these for kind of different things. So the main dispatcher on Android it's actually the main thread. And it's typically where you want like most of your coroutines to be living, unless they're one of the 2 other categories. So like a typical coroutine will start in main, and then switch out to the I/O dispatcher when it wants to do a network operation, when it wants to actually deal with the disk, like calling into room. And if you have like some expensive CPU stuff, like the classic example of calculating Fibonacci, which we always use in coroutines for some reason, or if you have to transform a list and it's too big to do that on the main thread, you can use the default dispatcher. And if you're looking at the slide, it's kind of curious. The default's for CPU, but main is for everything. It's like, how did this happen? Well, so on Android, this makes sense. Coroutines and Kotlin are also used on backend systems. And on the back end, the default dispatcher is totally like the right default dispatcher. But on Android, main is kind of a more reasonable choice because you usually start from main and end on main. So now that I've used with context and I've told coroutines I need to run this little block right here over in dispatchers.io, I can now make any blocking call I want in here. I can actually read from the network. I can talk to room. I can do whatever I want in here. And there's no chance that I will ever block the main thread. In fact, this is now a main safe function. No matter who calls this, no matter what thread they're running on, this function will always be safe to call. And this is like a huge transformative thing for Android development. Like I think I've written some crazy patterns in order to like build architectures to make sure I never accidentally make a database call on the main thread. This kind of makes it so I can encapsulate all that logic in a simple place. Now, if I look at this with context here, like, yes, it's great I have a mechanism to kind of switch threads using coroutines. But it would be kind of like tedious if I had to actually use with context dispatchers.io or with context dispatchers.default, like just constantly throughout my code base. It's kind of a big pattern. Instead, we can move this into libraries, right? We can, if you use Retrofit in a new version that's coming out soon, you can just make a service that exposes a suspend function. And if you do this, it's still going to execute literally the exact same way that you're used to with Retrofit with callbacks, except now you can use that style of coroutine call and you're going to get main-safe behaviors from Retrofit. And so this is like pretty awesome, like this ability to kind of simplify our code and replace callbacks with suspend and resume. And the key concept here is that when you make suspend functions, like when you make functions that make network requests, when you make functions that do large CPU operations, a good practice, a best practice, is to ensure that they're always safe to call from the main thread. And you can use that with context, dispatchers.io, dispatchers.default, in order to make sure that that happens. And that kind of covers the two main things that coroutines like give us as programmers. These are the problems that coroutines are really, really good at solving. They help us replace callbacks with a bit simpler code. And they allow us now on Android to kind of incorporate main safety into our APIs without having to transform them into callbacks or add something like futures or other patterns that solve this problem. So I want to kind of shift gears now. So we kind of covered the problem that coroutines are good at solving. Now I want to talk a little bit about the past. Like, how did we get to coroutines in Kotlin? So coroutines were not invented by JetBrains in the last 2 years and added to Kotlin. It's not the first programming language to have coroutines. And I think it's really informative to look back in history to see what was successful with previous languages and how coroutines have been used before to see how they might map into how we're going to use them on Android. So coroutines, the word coroutines comes from a paper written by Conway in 1963, which is literally as old as programming languages. So coroutines literally come from the first COBOL compiler implementation. So I do want to be clear, COBOL did not have coroutines or any features at all. But in order to write the compiler, they kind of had to solve some problems that involved a lot of asynchronous I/O, reading from file systems and transforming things into compiled programs. And they invented this pattern in assembly code of coroutines, and they wrote a paper about this idea, and the term comes from them. To give you some context of like how long ago this is like the very beginning of the space race. All right, so this paper defines coroutines as a function which communicates with other functions for both input and output. Raise your hand if that made any sense. 4 people. So that was actually a relatively confusing definition. And you actually see this through the languages through the early 60s, or the attempts to implement coroutines. This was relatively confusing and it wasn't like quite clear enough. So I'm going to give Conway credit for inventing the term, but I'm not sure I'm going to give him credit for like fully landing on the idea of coroutines. So moving on from the COBOL compiler, the next and first language to implement coroutines as kind of a language feature was Simula, which is this really, really, really fun language. It came in 1967. It's object-oriented. It has inheritance. It has methods. It has properties. It's all of the things you know and love from 2019 programming before the first moon landing, which is kind of crazy. It also had coroutines. In fact, it only had coroutines. It did not have functions at all, which is kind of weird. But it's how they thought it was going to be a good idea. I want to stop here for a moment, and like for the best of my knowledge, at least, no one has actually put coroutines on the moon yet. So, new life goal. So let's take a look at some Simula code. So Simula was commonly written on a small pile of punch cards, which we'll translate into a slide. So Simula is kind of an object-oriented programming language without functions and with coroutines. So let's take a look at what code like this looks like. And I want to kind of like disclaimer, I could not actually find a working Simula compiler when I was making these slides. So this may not compile in any compiler that currently exists, but it's a slide. So I'm going to make a class ping and a class pong. And you might kind of like have already thought about where this is going to go. I'm going to make ping call pong and pong call ping, and they're going to just do that back and forth. Let's write a couple lines of code in Simula and see how we might do that. So in order to call pong from ping, I'm going to need a reference to the other one. And from ping from pong, I'm going to need the reference back. And then what I'm going to do is I'm going to call detach. So this is a statement in Simula which says I would like to suspend my execution and resume the execution of whoever called me. And then later, whoever got that detach call is going to set up that reference and then call resume on one of these. And then once one of these gets resumed, this is just going to continue on and on and on and on until someone in ops kills this job, because this is an infinite loop right here. But the interesting part of this, like this very first language with coroutines, this is the first time anyone implemented coroutines in a programming language. We already see the characteristics of coroutines that are going to later in 2018 become part of Kotlin coroutines. So you can see suspend maps directly to detach, and resume matches directly to resume. That name actually just made it all the way through all 40 years. So the next language that was of interest for coroutines was this academic language, ACL. It's kind of this really very, very, very interesting academic paper that comes with a programming language. It was Marlin's PhD thesis in 1980. And I do recommend this paper because if you are very interested in historical coroutines, because it's a great summary of everything that happened before. And Marlin gave us this operational definition of coroutines, which would turn out to be the first operational definition of coroutines and the definition that we still use today. This is the definition of a coroutine. And it says that local data persists between successive calls, as well as execution is suspended and resumes where it left off. So this is quite a bit more clear than that paper from Conway, and we can now think about how this might work. If you keep going in the paper past about page 20, it gets a little weird though. So he again made a language with only coroutines, and he made this diagram, which is probably my favorite part of the paper. It's the structure of the solution to the telegram problem using coroutines. And this raises many questions. What is the telegram problem? Why is someone sending telegrams in 1980? And also, why would anyone code this many circles? That looks, I don't even know what that does. That's crazy. So moving on, so this kind of solved coroutines from an academic perspective. This is now an operational definition. They're well understood. He solved many, many algorithms with coroutines and demonstrated that they're a useful programming practice. And a couple academic languages used it. And then one, this is Lua, that was a little bit more practical. But basically, no one really touched them again until all of a sudden, in the year 2000, Perl gets coroutines. And this is wildly different than these other languages. Perl is a language you've probably heard of. And then simultaneously, in 1989, Perl was the way to write backend systems. So if you're writing a backend system, you were either using Perl or C++ if you wanted performance. And this is fundamentally caused because the internet's happening and coroutines are really, really good at this. So Perl defines it as a coroutine is a value returned by suspending and resuming. And to be honest, it was only kind of successful in Perl, but we move forward a couple years and we see Python gets it. And this is early in Python's timeline, but right after this, Python will become one of the main backend languages. So Python gets coroutines because coroutines are a natural way of expressing asynchronous I/O. And this is the first time any language has gotten coroutines for what would turn out to be the solution that we ended up finding useful for coroutines in the end. So I want to kind of go back to that example from the beginning. So here it is in Kotlin, and I'm going to translate it to Python. And let's walk through how coroutines are implemented in Python. And if you've never seen Python before, there's a couple differences. You'll notice they spell the word fun def, which is a choice. They also use colons instead of curly brackets. They don't have curly brackets down here. And this one's very, very important if you've never seen Python before. Those are spaces and not tabs. So the other thing that is going on here is we lost that suspend keyword that we were adding in Kotlin, and we gained this yield keyword right here. So this yield keyword is doing the exact same thing we're doing in Kotlin, but we put the keyword in a different place. So in Python, you have to say yield every time you want that suspend and resume operation to happen. Whereas in Kotlin, it's implicit. And this is one of the big things that Kotlin did to progress the state of coroutines. They kind of realized if networking operations are normal and we're going to be using coroutines to do them, maybe we don't need to decorate every single time we make a network request. And in fact, in reality, in practical code, forgetting this yield statement is very, very easy to do, having been a Python coroutine programmer, and it falls over pretty quickly. So let's see how this thing executes in Python. And this is a nice instructive example of how the dispatcher pattern came to be. This pattern was really pioneered by the Python backend community. So when I call onDataNeeded now, and I'm in Python, you might expect it's going to call the function. But actually, Python does something completely different because of that yield keyword we were talking about before. Instead, what it does is it gives me this thing called a generator. And in order to actually make a generator execute, I have to iterate over it. So I'm just going to put it in a for loop. And the first time that for loop executes, it's going to execute up to the first yield statement. And then at this point, it's going to call that network request thing. And network request has to return some sort of object. And then it's going to suspend itself and yield out the result of that network request call. So I'm going to call the object that it returns a suspend call. That's not a real name. It's not used in Kotlin or Python, but it kind of captures the idea. And then what you have to do is use that suspend call to somehow get a result. You can imagine maybe you're going to set up a callback in there in order to get the result from that suspend call. And then you can call send on that generator. And when you do that, it's actually going to resume the generator. So that result is going to be pushed into the coroutine. This is going to be pushed into onDataNeeded. And now I can assign that and show the result. All right, so after Python, 2007, Go, it's pretty famous for having coroutines, or Go routines as they called them. And then C++ gets coroutines in a library. And then this one is huge right here. C# gets coroutines in 2012. So I was playing with coroutines in Python at the time, and this was like a transformative moment. Python and Go had coroutines. We were playing around with it. We thought we were doing like fun things that were like totally outside of the mainstream. And then all of a sudden, Microsoft introduced this concept to their mainstream programming language that they shipped to millions of developers as the primary development language for Windows, which was like, wow, coroutines just became really big, and these things are now mainstream. And then we fast forward a couple more years, and JavaScript finalizes their coroutines in 2017. And then 2018, Kotlin and Swift get coroutines. So there's like a pretty clear story going on with this timeline. We have some academic interest, and the general pattern of coroutines gets solved very early on. It's one of the very first programming language design patterns that we figure out as a computer science community. Then it kind of like just falls off. Like even academia is not really interested in it for 20 years. And then all of a sudden in the year 2000, they start showing up in literally every single language. So like what happened here? And I think the answer is just really, really clear. The web happened. The internet happened. So if I ask this crowd right here, like everyone at DroidCon, who here had to write network-based programming in the last 6 months? I'm seeing all but like 4 people. So like this is what we do nowadays. This is a very normal programming practice that we all have to solve. And again, coroutines are a natural way to express I/O. They kind of lift this up to being a language level primitive and simplify our code. So this is why they're kind of taking off and being successful in all the languages. So this is like kind of like answering this thesis of like, are coroutines a fad? And my hypothesis, my theory is because of the internet, this is why coroutines are successful, and we're seeing them in every single language all of a sudden. And I would expect that over the next 10 years, we're going to see more and more coroutines, not less and less coroutines. So that's how we got to where we are today. Let's dive in a little bit to what is going on with coroutines right now, April 2019, in Kotlin. What has Kotlin added to the coroutine story, and how can we use them a little bit? But before we do that, there's kind of this interesting thing about coroutines. They're extremely rare to have been taught in school or introductory computer science classes. Who here learned how to use functions when they learned how to program? Everyone? Okay. Who here learned about call stacks and could explain to me how a function works with a call stack? About half the audience is like happy with that question. Okay, so here's a more interesting one, and this is like, I assume this is a little more esoteric knowledge. Who here has implemented functions in an interpreter or a compiler, maybe in like a computer science classroom project? So about 20% of the audience. So this is like a pretty, like, it's pretty like well known among like a small group of people. Then the next question I have, this one's quite interesting. Who here could explain to me how to implement coroutines? One person. We should chat afterwards. So I think this is really showing like a deficit in education in coroutines. And this kind of makes sense, right? Because coroutines just became very, very big in 2012. It takes a while for academic curriculum to be updated. I went to school long before 2012. And so when I was there, coroutines weren't even a word that you would talk about. Now, earlier in this talk, I showed this kind of operational definition of coroutines where I said it makes the rest of the function into a callback. And I love this definition because it like helps you map the concepts together, but it doesn't really help me understand how coroutines work. It doesn't explain kind of the mechanism at the same level that I understand how functions work. So what I'd like to do now is imagine for a second that we're going to have a Computer Science 1 lecture on how coroutines work. Hello, class. As a reminder, just a little bit of bookkeeping, I'm currently taking a sabbatical from email. So I won't be responding to your emails until 2020. Coroutines offer us an alternative flow control mechanism, and as you clearly saw from the previous slide, let's try that again. So I want to revisit really quickly. About half the audience raised their hand about explaining functions with stacks. I want to revisit how this is implemented. So I've made a little hello Boston function here, and I'm going to call it. So when I call this function, there's this call stack, and so what it does is it pushes a thing, it's called a stack frame, on there to track the fact that this function's executing and keep track of all of the variables that are in that function. Then, when I try to append this string Boston onto hello, it's actually going to call string builder.append. So again, it pushes a stack frame onto the call stack, and it runs that append code. Then that returns, it pops it off the call stack, and then I push printline onto the call stack. And for whatever reason, the variable to printline in the source code is x. I don't know who named that, but that's actually what it is. And then printline's going to actually print, then it's going to pop itself off the call stack. Hello is going to pop off the call stack, and that's how you call hello world, and that's how it executes. So let's jump back over into coroutines land and explain how to implement coroutines at kind of that exact same level of abstraction. So in order to do this, I'm going to add that call stack back again, and then I'm going to, for absolutely no reason at all, add a local variable x and assign it to 1, just because it's illustrative. So I'm going to go ahead and call this function. And in order to do that, I have to introduce a concept that I've chosen to call a suspend marker. This is just a point on the stack which says everything above here on the stack is executing a coroutine. And everything below here, it might be executing a function. And you'll see why this is important in a second. And you'll find that this is kind of a universal concept in all of the coroutines implementations. Then I call the function, and it executes the exact same way, right? So I call load data, and it pushes load data onto the stack. And then I assign x to 1, and it updates that local variable in the stack frame. And then I get to calling network request. And here's where I have to call resume. And I have to implement that resume, that suspend and resume mechanism. So in order to do that, in order to actually suspend my coroutine, all I have to do is copy that stack frame off the stack. So just kind of save it out over into kind of just a big unstructured bucket of all of the running coroutines, or all suspended coroutines. You might imagine this is going to be implemented in the heap. And then it's going to push network requests onto the stack as well, right? Because it actually calls network requests now. And then when it calls with context dispatchers.io, now we're going to suspend all of the execution on the main thread. In order to do that suspend, we again just copy the stack frame over into the heap. Then we are done at this point. Every single coroutine that we started on the main thread is suspended. And there's currently no coroutines happening in the main thread. The suspend marker can go away, and the main thread's unblocked. Now the network request can run. So it's going to be able to unblock the main thread. You're going to be able to make all of those on-draw calls. And the dispatchers.io is still going to be responsible for running that network request. And then fast forward 4 seconds, the network request comes in. It's going to have to resume. And the mechanism for this is kind of the inverse of what we did before. In order to resume, we add that suspend marker back. And we just restore that saved stack frame. And we just put it on the stack as if it's been executing the entire time. Network request completes. It returns. And then it resumes load data. It literally just copies that thing back, installs it back on the stack. My execution resumes exactly where it left off, right? Nothing has changed at all, except time progressed and my function got resumed. Then I continue execution. It's just like a normal function at this point. I assign the value data, and then I call show data. And that's kind of the mechanism, right? This is like kind of an abstract way to think about how to implement coroutines. This is an abstract way to think about how to implement coroutines, and allows you to map this concept of like moving all these stack frames around into taking a callback of the rest of your function. The other big thing that Kotlin added to coroutines is structured concurrency. And this is 2 complicated words that describe a complicated topic that is also very simple at the same time. So it has huge implications, even though the ideas are kind of simple. This is also something that's brand new. It's something we're still going to have to figure out. I showed you this timeline earlier where I showed like coroutines were a solved problem in 1980, and we've just been doing that again and again over since then. Structured concurrency comes from there. So structured concurrency was borrowed from Python and added to Kotlin coroutines. And it was introduced like a year and a half ago. So while a lot of people have a lot of experience with coroutines going back decades, Roman at JetBrains and a couple of people have a lot of experience with structured concurrency. So this is something we're going to have to really figure out, like how to use this thing and how to explain this thing even. So I'm going to take my best attempt to explain structured concurrency right now. But you know, if you figure out a better way to do this, please submit a talk next year and explain it to everyone better than I'm about to. So there's kind of this fundamental thing that real-world applications with coroutines. Like we've been using coroutines now in large production systems since 2004. Coroutines easily create work leaks. This is like kind of like a memory leak, except it can also use the CPU. Right, so this coroutine encapsulates kind of a suspended function that maybe resumes itself every now and then, uses a little bit of CPU, maybe a little bit of network, and then maybe suspends itself again. And this could be like an infinite loop. And this thing kind of accumulates over time, especially on backend servers that live a long time. But on Android phones, this can be a serious problem as well, where you start some work and then you lose track of it. So you can kind of think about this. Earlier I was doing that stack frame example where I was copying the stack frames from the stack over into the heap. I showed 2 coroutines, but it's very realistic to have like 1 million coroutines. So if you try to think about like, how are you going to keep track of that? Like, what is your code going to look like to keep track of 1 million things that are all stored out in the heap, that all possibly resume execution, possibly via mechanisms that you don't currently have a reference to? This is a pretty hard problem, and structured concurrency takes a stab at solving it. One of the ways, this is kind of a little bit of a second tier of structured concurrency. It solves leaks. And then it also provides us with a kind of a new guarantee that was not present in any previous languages. When a function returns, it has completed all work. This is like not a controversial statement. Like we all agree that functions don't continue executing after they return. Okay, yeah. And like this doesn't have to be this way. This just happens to be the way every single programming language ever has always implemented functions. And the reason for that is because it makes our code easier to reason about, it makes our code not surprising, and it makes our code like very like easy to read. Kotlin extends this by giving us a new guarantee that when a suspend function returns, it has also completed all work. And this is a completely novel guarantee that Kotlin has added with structured concurrency. So let's take a look at how that's done. What did Kotlin do in order to build this big concept of structured concurrency and help make our lives easier with coroutines? So I'm going to go back to that load data example, and I'm going to try to call it. So if I'm just in some function somewhere, and I try to call load data, it's going to give me an error. It's going to say that the suspend function load data must be called from a coroutine. And you might be thinking in your head, Sean, you've been telling me suspend functions are coroutines this entire talk. What is going on here? So the thing is a suspend function is basically just a function that can run in a coroutine, but it doesn't itself start a new coroutine. In order to do that, you have to use one of the builders that kind of transforms you from the function world into the coroutine world. Typically, you're going to use the launch builder. And this is exactly the same thing as like thread.start or executor service.submit. It basically just like starts a unit of work and like lets it run. And then inside the lambda that you pass to this launch block here, you're able to call any suspend function because you've been transformed from a regular function world into a coroutine world where you can now call suspend functions and get that suspend and resume behavior. So this is pretty fine. Like things are like, you know, going okay here. But let's go crazy. Let's go ahead and make a function called load lots. And what this is going to do, it's going to repeat 1,000 times, and then it's going to launch 1,000 coroutines. And each one of those coroutines is going to call load data. So now I've kind of moved it out of this realm of like we have one thing to keep track of, and now we have 1,000 things to keep track of. And this raises lots of questions. The first one of these is, if I don't need this work anymore, who is going to cancel that work? How are they going to cancel this work? Imagine the user navigated away from this very heavy screen that makes 1,000 network requests, and we no longer want to complete these network requests. What mechanism can we use to do this? The other big question that is going to come up is who gets exceptions? If you start 1,000 network requests, you're probably not going to get 1,000 network replies. You're probably going to get like 998 network replies and 2 exceptions. Where do those exceptions go? And the other big question that needs to be answered, Why is your Android app making 1,000 network requests? Please don't do that. Coroutines are great at 1,000 concurrent things, but I don't know about network requests being the thing they're doing. To solve this, Kotlin introduces the idea of scopes. In Python, this idea was called gardens. I think scopes is probably a little bit more Kotlin-y. So scopes keep track of your coroutines. So even though we're starting 1,000 coroutines, we can put all of those coroutines into one scope. And then there's this really cool feature that scopes give us on on Android that allows us to cancel all of the coroutines that scope is keeping track of. So if you think back to that example where we're just copying stack frames out of the heap, now I have 1,000 things out in the heap. There's no real structure to those, except some scope somewhere knows about each one of those and has the ability to cancel it, which is fantastic. So how does Kotlin actually do this? How does it implement this? What's the mechanism that the language uses in order to make these guarantees? So when I wrote this little example function here, I said launch load data. I was lying to you. This doesn't compile. This function right here, again, we get a compiler error that says undefined function launch. In order to kind of like put a coroutine in a scope, every time you start a new coroutine, and you do this with a function like launch, one of the coroutine builders, you have to define a scope that it runs in. So let's define one of those scopes. I can make one a coroutine scope dispatchers.main, which if that seems quite verbose to you, you can also spell that main scope, which is a thing we introduced immediately after we realized the other thing was too long. Then main scope does exactly the same thing. It makes a coroutine scope that will, by default, run on the main thread. Then, to actually launch the coroutine, you just say scope.launch. And now, the coroutine is going to execute in that scope. If I put this in a view model, or something that has a life cycle, I can do something really, really magical in Android to make this all kind of work together in this awesome way. So in a view model, I might override onCleared, and then onCleared, I can cancel that scope, and then every single coroutine that scope has started, or is keeping track of, will be canceled. Even if I made 1,000 or 1,000,000 coroutines in this view model, they're all going to get canceled, and I can do that with one line of code instead of iterating over 1,000,000 coroutines and trying to cancel each one of them at a time. So this is fantastic. Like, this is a really, really nice abstraction to add for Android. You might be thinking, that's a lot of boilerplate, and again, yes, it is. So, coming soon, all of that code is going to turn into an extension property on ViewModel called ViewModelScope, maybe. It's an alpha, but that's what it's called today. Normal alpha disclaimer, it may have bugs, and it may change its name before it gets to production. So use at your own risk. So this is a way to make a coroutine in a view model. But the key concept here is even outside of a view model, we can think about launch starts a new coroutine in a scope. And this helps us deal with kind of that leak problem that we were talking about before. How do we do this guarantee, though? How does Kotlin give us the when a suspend function returns, it has completed all work? So let's try to make this load lots functions again, right? So now I'm going to transform it just a little bit. I'm going to make it a suspend function. And if you kind of think through the implications of what it means for that to be a suspend function, that means that someone somewhere has started a coroutine, and that coroutine is in a scope, and has then called this suspend function. I don't know who did that, because I'm a function, I don't know anything about my caller. But I do know, as a truism, that someone had to have a scope and a coroutine running in order for this function to be called. However, even though this is a suspend function, it must be running in a coroutine. If I just try to call launch from here, I'm again going to get this undefined function launch. Now, one way that you could just kind of like fix this, like there I fixed it, is to just go ahead and call global scope.launch right here, which, so what this does basically is just launches 1,000 coroutines that no one's keeping track of, and no one hears about the exceptions, and no one has the ability to cancel. And it's genuinely scary to me that this code exists. So instead, there's a better way to do this. What I really wanted to do is, instead of kind of like making a new scope and like launching coroutines off into the other, I want to make a scope that's based on the scope that called me. I want to make a new child scope of whoever. It could be a view model. It could be work manager. It could be, I don't know, a service. And it could be some other scope somewhere in my application is calling here, and I want to make a scope that's a descendant of that. The big difference between this and the last time I wrote coroutine scope is this has a lowercase c, Just for maximum clarity, those APIs differ by exactly one character. So when I do this, I can actually then call launch inside the coroutine scope lambda. And each one of these launches is going to be tracked by this child coroutine scope that I've just defined. And there's one more really, 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 really awesome guarantee that this coroutine scope gives us. And that is, it's going to wait for every child coroutine that's launched in this scope, which is absolutely awesome, right? So now you can be guaranteed when load lots gets called, even though it makes 1,000 network requests, which is still a questionable decision, we know that it will have completed all 1,000 network requests before it returns. And this makes everything just much easier to reason about and gives us that guarantee that when a suspend function returns, all work is done. So that's structured concurrency, and that's my stab at trying to explain structured concurrency. I look forward to reading your blog posts if you come up with a better way to explain it. Sometimes, though, on Android, specifically on Android, we want to do things that aren't structured concurrency. And this is kind of like a detail of being in an application that's on a UI and a user's interacting with. Sometimes what we want to do is actually start work that just runs and kind of in the background, and we don't want it to cancel when the user goes away. We could think about this, for example, I might have like a form save. I might have a user profile, and there's a save button or a back button, and both of these are going to cause a network request that saves the user profile. But I don't want to like hold the user captive on the screen while that network request is happening. I want to let them leave. I want the view model to get canceled, but I want this request to continue going on in the background. In order to do this, you kind of have to like break the guarantees of structured concurrency. So one way to do that is you could just use global scope, but that's kind of scary in its own way. But when you go down the path of figuring out how do I do unstructured concurrency while still kind of keeping my code safe, you quickly realize that as you add more scopes to execution, you multiply the complexity of your code. Like, really, it's like a multiplicative effect. You add 2, it's hard. You add 3, it's very hard. You add 4, just give up. So it's one of those things where you want to kind of like, if you can do it, if you can stay in that view model scope, if you don't need to unstructure your concurrency, things are really easy. Things work very similarly to functions, and things are awesome. But sometimes you need to do that thing. You need to do that background save. So I'm going to show the code for a brief second. This is one pattern that allows you to do that background save in a safe way. So I'm not going to like dive through this code, but all it does really is add a timeout and make sure that only one save is running at the same time. But what the important part of this code is, there's only one line of this code that's actually my application logic. Everything else there was just using kind of these low-level coroutines APIs in order to implement that timeout and implement that single execution thing. And I like to imagine this code like living in a repository somewhere, and I like to call it artisanal bespoke concurrency, which is a great combination of adjectives to apply to bread and a terrifying combination of adjectives to apply to concurrency. And what's fundamentally missing here is that we're using the wrong level of abstraction. Coroutines kind of give us this low-level abstraction around how to do concurrent work. They are kind of at this level of like threads and mutexes, but you don't like mix those with your application logic. Like, who here launches a new thread every time they want to like make a database operation? Right, we don't do that. So what you want to do here is add some sort of structure to your unstructured concurrency. You want to build abstractions in your application code that allow you to kind of express what you're really trying to do. And then at the same time, this gives you the ability to like test these expressions really, really thoroughly. Like, now I can make sure do save is correct, and then I use that in my repository. And to be honest, I'm much happier writing these 3 lines of code in my repository than that whole slide I showed earlier. And so is the next intern that reads my code. So we've talked about the past and how we got here. We talked about how coroutines probably aren't a fad because the internet seems to be sticking around. We talked about where Kotlin has progressed the state-of-the-art of coroutines. So where are we going to go? Like, where is coroutines? What's the future of coroutines on Android? Or just in general? So right now, most popular languages have coroutines already. If you tomorrow decided to switch ecosystems and you picked any of the languages in the top 20 randomly, you would find coroutines in a little bit over half of them. So you're probably going to be dealing with coroutines in any language. And when we look at new languages, they're launching with coroutines as kind of a default feature. It's something that is like table stakes for introducing a new language in 2019. Just last week, I saw a new language launched on Hacker News. It looked really, really cool. That had copied coroutines from Kotlin almost exactly. And I was like, wow, that's pretty cool to see these ideas being copied forward. So it just really seems like adding coroutines is just something that people expect. And the reason for that, again, is because coroutines are a natural way of expressing asynchronous I/O. Kotlin adds this big concept of structured concurrency. It's kind of this huge radical shift in the way coroutines work. If you go learn another language coroutines that doesn't have structured concurrency, leaks and these guarantees about exceptions just aren't present. It's also kind of a big deal. And we're going to have to figure out how to explain that in the Android community and in the Kotlin community. We're going to have to figure out how to style our code and what sort of good patterns exist and share that with each other. But it's kind of an awesome idea. It's one of those really big ideas that could be a really, really good idea because it makes code easier to write, read, and reason about. It also makes the suspend functions behave very similar to functions. In fact, so similar to functions, it kind of raises the question, do we even need functions anymore? So if we kind of think about it, like functions now are just a micro-optimization of suspend functions. They don't do that copy behavior, but maybe structured concurrency gets us there. And no, that's crazy. Maybe I've gone off the deep end there. But I think there's going to be an interesting question. And this is something that like, we're all in the Kotlin community going to be exploring over the next couple of years. And 10 years from now, we're either going to look back and see this as the beginning of structured concurrency and it's an awesome idea that's everywhere, or it's going to be checked exceptions, and maybe it wasn't such a good idea, but it seemed like a good idea at the time. On Android, libraries are very quickly gaining coroutine support. So we already have Room, Work Manager, Retrofit. View models are getting some coroutines. And we can expect that every callback-based library will start exposing coroutines soon. And you can expect to start seeing more scopes based on life cycles as well. But the future of coroutines on Android is really literally everyone in this room. It's you are in your hands because the community will determine where they go on Android. And this literally means each of you. So if you're looking for a way to get more involved in Kotlin, in Android, this is really a perfect time. Like we're really at the beginning of the coroutine story on Android. And there's just absolutely so much you can do to get involved. So even if you just learned coroutines in this talk right now here, you could share what you learned and what you understand about coroutines with the way that you understand it as someone who just learned coroutines. Because your perspective may help someone who's just learning coroutines for the first time as well. And that may be like something that really, really helps the community move forward. Blog posts are totally the way we're going to figure out the best way to use coroutines. We're going to have Twitter, we're going to have blogs, we're going to have conference talks. We're going to use coroutines inside of our apps, inside of our companies, and we're going to talk about how to use these as best practices. And we're going to grow together as a community and figure out how these things work on Android. So as you start maybe playing with coroutines inside your company, consider writing a blog post about your learnings, like what worked and what didn't work. And as we move forward throughout this year, I think we'll start seeing people maybe kind of the common things that worked, and those will turn into patterns. These are going to be the ways that we find that work to use coroutines on Android, and we're going to find things that don't work, which eventually become best practices, and then libraries. So writing a library, I genuinely am suggesting that you should consider writing a library for coroutines. But writing a library might seem really scary if you've never done it before. But honestly, it's just code, usually not that much code. And we're going to need libraries about coroutines to kind of elevate the abstraction level from kind of this low-level thing that we have today into stuff that matches exactly what we're doing in Android apps. There's just a bunch of common things that come up with coroutines in Android, and everyone's going to have to solve them, and they're probably going to solve them very similar ways. So if you have some really cool ideas about how to deal with structured concurrency or unstructured concurrency on Android, you can put that out there as a library, and you can get feedback from the community, and maybe it's going to be a really cool and popular library, and everyone's going to use it. The other thing that's going on in the future is RX coroutines. So every time I've talked about coroutines until now, someone has asked me about what about RX Java versus coroutines. And my answer has always been that they really solve completely different problems, and someone's probably going to write RX coroutines later this year, which is, of course, just RX Java backed by coroutines. Well, that answer is so last week. JetBrains put Flow into alpha last week. So it implements many of the ideas of RxJava using coroutines. So if you're interested in checking out this integration, you can go try them out in the current coroutines alpha. They're really cool. I'm very impressed by the code, and I think that it's going to be a really interesting API to use. I haven't played with it yet. I just kind of read through the thing. But I'm pretty excited to see what everyone here discovers and learns about them. And if there's one thing you take away from this talk, it's that Android loves coroutines. They have the opportunity to make Android development easier, more approachable, and more importantly, it can help simplify our code. And with that, let's suspend for the day because I heard there's an after party.